9 Olympic swimming pools gone every single minute. That is what 97,000 gallons per second really looks like. Today we are stepping inside a powerhouse built for one thing, moving water at an enormous scale. 5 identical joints sits in a row, each one capable of pushing nearly 300 megawatts, not by spinning fast, but by forcing huge volumes of water through a massive runner. Slow speed, huge diameter, pure force. No towering waterfall, no dramatic drop, just a 69 meters of head and a river being guided through steel. This is a low head hydropower. Power doesn't come from height here, it comes from the flow. But before any of that powers appears, the real challenge begins. The rotor weighs hundreds of tons. It is resting on thrust pads, completely still. If it turns dry even for a moment, the damage is instant. So first it has to be lifted. A high pressure oil jacking system activates. Oil is forced beneath the thrust bearing pads. The rotor rises just a few microns, invisible to the eye, but now a thin oil film separates metal from metal. That microscopic gap makes motion possible. Only now the machine is allowed to move. Upstream, water waits, silent, controlled. The governor sends the command. Hydraulic servos respond. Guide vanes begins to open slowly, evenly, like a joint breathing in. There is no sudden yap, no violent surge, because at low head, velocity is lower, but the volume it is massive. Water floods into the runner, torque begins to build, not a kick, but a steady push. The shaft starts running heavy, slow at first, then smoother, stronger, and the tachometer climbs to 20, 40, 70. And all this time, the governor is constantly watching. You can see it in the wicket gates ring. The vanes don't just open once, they adjust continuously, opening, then slightly closing, then opening again, because the governor is holding one thing constant, that is speed, and it is 100 rpm here. If the turbine turns to accelerate even slightly, the governor reacts instantly, reducing the opening, less water, less torque. If the speed drops, it does the opposite, open more flow, more power. A constant balance until the shaft reaches 100 rpm. Then all it needs just 100 revolution per minute to produce great frequency. Because this machine trades speed for size, massive runner, wide passages designed to extract energy from sheer volume. And as it spins, something invisible begins, excitation. So direct current flows into the rotor, a magnetic field forms and rotates within it. As this magnetic field cuts through the stator winding, voltage is induced. No spark, no noise, just electricity being created. Now the machine is alive, but it is not yet connected to the grid. To join to the grid, everything must match perfectly. Voltage, frequency, phase angle. Even a small mismatch can create a massive shock, and with this much rotating mass, that shock is amplified. So operator waits, watching, measuring, timing. The breaker closes. Instantly, the machine locks into the grid, and now comes the real loading. Guide vanes open further, flow increases, the same governor that controls speed now controls power. As load demand rises, the vanes open more, water flow increases, torque builds, but the moment speed tries to drift even slightly, the governor corrects it, closing just enough, opening just enough, always balancing. Flow rises towards nearly 9 Olympic swimming pools every minute. Torque increases, power builds 50, 100, 180, and then it is stabilized at 250 megawatt because today target is 250 megawatt. Steady, controlled, and continuous. But beneath that stability, everything is being watched. Thrust bearing temperature, shaft vibrations, oil pressure, every signal matters because uh, in Francis turbine and heavy machinery, stability is everything. There's so much stored energy in that rotating mass that if the load suddenly drops, the speed can surge dangerously fast. So protection system stands ready every second. This isn't explosive power, it's a controlled power. A river slowed down, guided, and converted into electricity at an immense scale. And all of it comes down to one thing: flow. But what happens when that flow is forced to stop?